Hello everyone and welcome to Coding Through Football. In football, a single moment can change the course of a match. Those fine margins make football both fascinating and unpredictable. But today we will explore whether we can bring some structure to that uncertainty. In reality, predicting football scores is quite challenging. Football matches depend on an enormous number of variables from game strategy and player roles to weather conditions, refereeing decisions, and sometimes even pure luck. Together, these factors make the problem highly complex. So, to approach this problem, we'll begin with the simplest case. Suppose there are only two teams, blue and red, who are equal in strength. Here are the results of the last 5 matches between them. Focusing on Team Blue, we can compute their average goals per match, which comes out to 2.2. But a team can't score 2.2 goals in a match, so an average alone isn't enough. Hence, instead of a single value, we will need a probability distribution, one that tells us the likelihood of scoring a certain number of goals. This is where the Poisson distribution comes in. The Poisson distribution is usually applied to discrete events that occur independently over time at a known average rate, such as arrivals at a queue, product defects, or goals in a football match. Its probability mass function looks like this. Here, E is a constant, X is the number of goals, and lambda represents the average goals per match. Therefore, if a team scores an average of 2.2 goals per match, we can set lambda equals to 2.2 and compute the probability of scoring exactly 0 goals, 1 goal, 2 goals, and so on. The Poisson distribution is defined for whole numbers from 0 to infinity. However, as we move further away from the average lambda, the probabilities quickly become very small. So in practice, we can truncate the distribution and focus on the first few outcomes, such as 0 to 7 goals. As we increase the value of lambda, the distribution shifts towards higher goal counts, and as lambda decreases, it shifts towards lower goal counts. Now that we understand the concept, let's implement it in code. We begin by importing the necessary libraries. Next, we define a function for the Poisson distribution. This function takes two inputs, x, the number of goals, and lambda, the average goals per match. It returns the probability of scoring exactly x goals given that average. Using this function, we compute the probabilities for each possible goal count and store them in a numpy array. Finally, numpy's random.choice function allows us to sample discrete outcomes from a specified probability mass function, so goal counts with higher probability are selected more frequently. However, when we run the code, we notice a problem. The probabilities no longer sum to 1. Any valid probability mass function must sum to 1, so something is clearly missing. The issue comes from truncation. By limiting the goal counts to 0 through 7, we have excluded the small but non-zero probability of scoring more than 7 goals. To fix this, we renormalize the distribution by dividing each probability by the sum of all probabilities in the truncated range. After this normalization step, the probabilities sum to 1 and the simulation runs correctly. Next, we define a function that takes two team names as input along with a parameter n representing the number of matches to simulate. By default, we set n equal to 1. If we simulate 5 matches with England as the home team and France as the away team, the model generates 5 corresponding score lines. Now, let's replace France with San Marino. The results immediately highlight a limitation of this approach. Since both teams are modeled with the same average scoring rate, the simulation does not reflect the difference in relative team strength. As a result, the high goal counts for San Marino appear more frequently than they realistically should. To address this issue, we introduce a simple heuristic to estimate relative team strength. We use FIFA ranking points as a proxy for team quality. While imperfect and not fully representative of true team strength, they provide a reasonable first approximation. We now introduce 3 additional inputs: the home team's points, the away team's points, and the strength factor. Instead of a single scoring rate, we define separate Poisson parameters for the home and away teams. Starting from a base scoring rate of 2.2, we adjust each team's lambda according to the differences in their ranking points. The home team's lambda increases when it is stronger than the away team, while the away team's lambda decreases accordingly. This results in two different probability distributions, one for the home team and another for the away team. The strength factor controls how sensitive the model is to differences in team strength. Larger values lead to smaller adjustments, while smaller values amplify the effect. At this stage, we encounter another issue. Some of the computed probabilities become negative. To understand why this happens, let's take a look at how we compute the lambda for the away team. When we plug in FIFA ranking points for England and San Marino and choose a strength factor of 300, a large difference in points causes the adjusted lambda for San Marino to drop below 0. A negative value of lambda is invalid for the Poisson distribution, which requires the rate parameter to be strictly positive. To resolve this, we impose a lower bound on lambda. Setting lambda equal to 0 is not an option because it would collapse the entire probability distribution to 0 goals. Instead, we clamp lambda to a small positive value using the max function. This ensures that lambda always remains valid while still allowing the model to reflect large differences in team strength. After applying this constraint, the simulation produces realistic match outcomes once again. We can now experiment with the model parameters. Let's try Japan and Ghana by plugging in their FIFA ranking points. When we run the simulation, most of the outcomes favor Japan, which makes sense given their higher ranking. Next, we adjust the strength factor. Lowering it to 100 increases the influence of the ranking difference, so the results lean more strongly towards the stronger team, Japan in this case. Increasing the strength factor to 500 reduces this influence, adding more randomness and leading to greater variation in the score lines. A value around 300 feels like a reasonable balance for now, but in a future video we could try optimizing this parameter using historical match data. We will end the video here. Today we explored how a Poisson-based model can be used to simulate football score lines using probability theory. We began with a basic Poisson distribution and gradually introduced heuristics to account for differences in team strength. That said, this approach has clear limitations. It assumes independence between goals, relies on heuristic strength estimates, and does not capture tactics, game state, or in-match dynamics. Still, it serves as a useful baseline and is foundation for more advanced models. Perhaps in future we can try learning these parameters from historical data or applying machine learning to model more complex relationships. If you have ideas for improving this model or would approach this problem differently, I would love to hear your thoughts. In future videos, we will build on these ideas and explore more advanced approaches.